Good morning. So I'll post those details for the Learning Center. They always change the name. So it used to be the Learning Center. Now it's the Success Center. It's all the same. It's free tutoring. So, like Kate said, she seems to be there kind of all day, hanging out. And of course, if you're just dropping in, then she might be available or soon to be available. So so really, really awesome thing to have, especially because like I'm always available too, but I mean, I know it's kind of intimidating to ask me questions maybe, or maybe the way I explain things, it just doesn't click. And that's totally fine. So Kate actually, she's really good about explaining things in different ways. Like she has visual things that might help. And so she's been doing this for some time. So really impressive stuff. So, and of course, can't emphasize this enough, it's free, so it's great. All right, so let's see here. Yeah, just the whiteboard. Here you go. Check it out. Yeah, it would take me forever, constantly erasing. But yeah, so let's see here. It's like how Sal Khan is always able to keep everything on one page. I just don't understand it, but anyways, on Khan Academy, I guess maybe she's like that. So what were we doing last day? Oh yeah, so for review here, we started, what did we do? Oh yeah, we finished, that's what we did. We finished polynomial long division. And then we got into rational functions. Rational functions. And we actually went through all those steps for graphing, or sketching, I should say. Graphing to me is the actual graph, whereas what we're doing is sketching. We're not paying that close attention to the exact points. So we're not plotting points necessarily. We're just we're sketching this thing so we can see what it looks like. So just as a part of our review, even though, so we did spend some time, or a lot of time last day, but a rational function r of x, we can write as p of x over q of x, which is just a polynomial over a polynomial. Polynomial over a polynomial. Okay. So to sketch a graph of this thing, there were multiple steps that we were going to follow, right? We were going to find things like the intercepts, so the x-intercepts and the y-intercepts. We were going to find, and let me try to do these in order, the vertical asymptotes, and followed by the horizontal asymptotes. And then we'll put all that together and have a sketch of a graph. So our steps, the steps to graphing r of x, right, where r of x is a rational function. The first step we have is we're going to factor. Now, I'll bring it up again later why, so at each step, why we want to factor. It just makes it easier heading down to find things like the vertical asymptotes, and the x-intercepts, right? So if we factor both the numerator and the denominator, it's going to be a lot easier later on. So we're going to factor the numerator and the denominator. Right? So that's going to be your first step. And if you have a look at some of those problems that are on the handout, some of those are already factored. So maybe to start, maybe it's nice to have a look at those first and then build up to the factoring. Or maybe you feel strong in factoring already, then that's great. So the second step is to find the intercepts. The intercepts, well, you have your x-intercepts, and that is where, well, the x-intercept technically is where y is 0, right? But it's also where the numerator, and we talked about this last day, so I'm just going to mention it here, but if it's a little bit cloudy because it was, I want to say like almost a week ago, right? Thursday. So if it's feeling a little bit hazy, maybe go back and review from last day. But the x-intercepts are where the numerator is 0. Where the numerator equals 0, right? And that doesn't look like numerator, does it? Not a lot better, but a little bit better. So it's where the numerator equals 0. And that's why it's so nice to have factored the numerator already, because then you can easily pull out those x-intercepts. Okay, so that's where it crosses the x-axis, right? And then the y-intercept is where x is equal to 0. Where x is equal to 0. So what you do is you have r of x is equal to y, right? And so really what you're actually finding here is r of 0, right? Evaluate that rational function when x equals 0. So we've already got a lot of information just from the intercepts, right? We know where it crosses the x-axis. We know where it crosses the y-axis. Usually it's only one y-intercept. Actually, it will only be one y-intercept, so that's nice. Great. Our third step is to find the vertical asymptotes. Now, let's see here. Let me try to summarize here. The vertical asymptotes, which we'll abbreviate to VA, vertical asymptotes. The vertical asymptotes are going to happen where the denominator is 0. So again, that's why we had to factor. It's because later to find those vertical asymptotes, that's going to be the easiest thing. If we've already factored it, then we've done a lot of that work already. So vertical asymptotes, so VAs, happen at values of x that make the denominator 0, right? So remember, you can't divide by 0, so you have to pull those out. So that's where you're going to have these kind of vertical asymptotes. Maybe they're heading up towards infinity, or maybe one's going down to negative infinity and one's going up to positive infinity. So that's our next step, is finding out the behavior around these values of x. So vertical asymptotes happen at values of x that make the denominator equal to 0. So then we need to find the behavior. We need to find the behavior around these values of x. And I'm going to do a little kind of sub thing. How we're going to do it is we're going to use a number line, right, and test values. So use a number line with test values. And I think that's where we got to in our example last day. We'll do a run through and then we'll pick up at that point from last day. But I just want to outline the steps first. So those are our vertical asymptotes. Now, our fourth step, and I would argue our last step, unless you count sketching, doing the actual sketch as a step, is the horizontal asymptote. Horizontal asymptote. Singular, which we will abbreviate HA, Hells Angels. No. Horizontal asymptote. So what we have is we're going to have our R of x, so our rational function is a polynomial over a polynomial, right? And so if R of x is equal to a subscript n, x to the power of n, plus da 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 da, we're only concerned with our leading term. And then I think they use b subscript m, x to the power of m plus da 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 da. So the degree of the numerator is n, and the degree of the denominator is m, as in Michael. And then we have these leading terms. So how we're going to determine these horizontal asymptotes is you're going to look at the degrees of the numerator and the degrees of the denominator. And if n is less than m, then you have a horizontal asymptote at y equals 0. If n is equal to m, then you have a horizontal asymptote at y equals an over bm. So notice that these are the leading coefficients, right, over each other. So if n and m are equal to each other, then your horizontal asymptote is going to happen at just a over b, right, the leading coefficients. And then if n is greater than m is our last option, then there is no horizontal asymptote. And there is no HA. And that's not one word. I don't know why I can't write today. But I can't. And then our final step, step 5 here. So we didn't really do any exercises with finding the horizontal asymptotes, but I think what you'll find once we do a couple of examples is it's really quite a lot simpler than the vertical asymptotes. To me, finding the vertical asymptotes and their behaviors is probably the hardest part. So then combine the information in a sketch. I kept it all on that one page, feeling pretty proud of myself. Okay. So from last day, I just want to summarize. From last day, what did we find? We found, so we went through and we did we were working with, oh, sorry, it's just catching up. We were working with this function 2x squared plus 7x minus 4 over x squared plus x minus 2. So first thing we did was we went ahead and we factored this thing. These are both quadratics, right? We know how to factor quadratics, and so that's great. So I'm not going to bring that work in, but I will bring in this guy, copy. So we had step 1, factor, and paste. Okay, and I'll just highlight it again. Step 2 was to find the x-intercepts first. So we went ahead and we said, okay, well, that's where the output is 0, right? And so we know from the roots that we have x equals -4 and x equals 1/2 are our x-intercepts. And then we found our y-intercept to be at y equals 2. So I'll just summarize that here. Step 2 is our intercepts. So our x-intercepts, we found were at x equals -4 and x equals 1/2. And our y-intercept was at y equals, I want to say +2, but I just want to make sure here. Go back. Yeah. Wow. -4 and 1/2, and then +2. Okay, so then we had our vertical asymptotes. Now this is where I want to pick up and kind of start fresh. We started doing this one and I kind of sent you on your way, but now let's kind of rein it back in and go through it and do it properly, because like I said, this is probably the hardest part of doing these questions. So I want to take it nice and easy. So here, so this was from last day, and now I'll do kind of the end of the review and continued here. So we'll say step 3 is the vertical asymptotes. So vertical asymptotes, or VAs as we'll call them, VAs happen at values of x that make the denominator equal to 0. Values of x that make the denominator 0. So good thing we have the denominator factored already, right? Because now we see, okay, the denominator is x minus 1 times x plus 2. So, or if you wanted to, at this point, if you wanted to skip the factoring, you would still have to do it, right? You would still have to factor to find your x-intercepts and then factor to find your vertical asymptotes. You could do it that way. It's just easier if you just get the factoring over with, but either way, you're going to have to do it, so it doesn't matter. X minus 1 times x plus 2. So the denominator in our case x minus 1 times x plus 2. So what does this mean? It means that at x equals 1 and at x equals -2, we have these vertical asymptotes. Okay. So what you're going to do, uh-oh, I'm going to need more space, aren't I? All right. maybe I'll bump this up and I'll bump this up just to give myself a little bit more space for, it's just because I've got this page breakdown here and I want enough space to do my number line with these test points. And that should be enough. So I know my points are at x equals 1 and x equals -2. Of course, I have to list them in order on my number line. So what I'm going to do is I'm going to draw my number line here. And this is going to be similar to what we did with inequalities, right? Where is this thing above the x-axis or where is it below the x-axis? Kind of same idea, except now we're going to try to figure out the behavior if it's going to positive infinity or negative infinity, because one of those two will happen. So, okie dokie, artichoke. I'll put a point at -2 and I'll put a point at 1. Now, what I want to do, and I want you to do in your mind, is to break up the space, because we're going to have to do 4 calculations. So we do 2, and I shouldn't have said calculations. We do work around both sides of these points, right? Because I want to know, how does it behave approaching -2 from the left? And how does it behave approaching -2 from the right, right? They might be going like this, like kind of one up and one down, right? So we want to look at the behavior around each of these points. So I'm going to split up my workspace here, but then I also want to split down the middle, because in this space, I'm going to be approaching -2 from the right. And in this space, I'm going to be approaching 1 from the left. Okay, so what I'll do is here, as x goes to -2, do you remember the notation that we use to denote from the left? We use a little negative in the superscript. Okay. And here, x is approaching -2 from the right. So then we use a little plus in the superscript. Okay. Here, x is approaching 1 from the left, and here, x is approaching 1 from the right. Okay. So these are the 4 regions that we have to look at. So you can do it with actual values, or you can kind of just think of values in each region, right? And so, but if it helps you to pick a value like -2.1, for example, and then plugging that value in into the original function, that's great, you can do that. But what we need to do here is we remind ourselves that r of x was, and that's just, so we need to use the factored version, 2x minus 1 times, and I'm just going to copy this maybe. Otherwise, I'll be scrolling back and forth all day here. Paste, shrink. Okay. So what you can do is you can pick a value that's close to -2, but to the left of -2, right? So -2.1, remember on the number line, right? So negatives are tricky on the number line, right? You have to kind of think about where you are, or at least for me. And so here you might pick something like -2.1. And then what you want to do is you want to plug in -2.1. And all we're looking for is if we get a positive or a negative result, right? Positive result means that it's going to be heading to positive infinity, and a negative result means that it's going to go to negative infinity. Remember, those are our only 2 options here, right? So it will go to infinity, it's just which direction, positive or negative. So here I'll write only looking for positive or negative. So in your head, you can do something like, okay, pick maybe a test point of -2.1. And maybe here in this region, maybe use 1.9, right? So values close to -2, but not at -2. Okay. So here, if I do -2.1 in here, then I would get 2 times -2.1, that's -4-ish, right? -1, so that's going to be negative. Okay, and so what I get is this is going to be a negative value times -2.1. So remember, in your head, you can just pick any value, right? That's just slightly to the left of -2. And if it helps, use a specific value like I'm doing. So -2.1 plus 4, that's going to be positive, right? Regardless. So it's going to be positive over, and remember doing this with the signs before, right? A negative times a negative makes a positive, and so we'll know if it's positive or negative, right? So we're doing the same thing that we did before, just slightly different context. So -2.1 minus 1 makes a negative, and then here's where it becomes the most important, right? -2.1 plus 2 is still going to be slightly negative, right? Because it's always to the left of 2. Okay, and so here I have a negative times a negative, which overall, right, a negative times a positive is a negative, over a negative times a negative is a positive. So a negative over a positive is going to make a negative. Now here, that's where you need to remind yourself of the rules of negatives. But what does that mean? It means that coming in from the left of -2, I'm heading in the negative direction. And so this is saying, well, then around -2 from the left, it's heading down like this. Yeah. Now let's do the same thing heading towards -2, but from the right now, right? So I have picked a value, -1.9. It doesn't have to be that, but it's a good value. The risk is if you're too far away. So before, right, we were just looking for the overall direction, or positive or negative. So then we would pick a value like 0. But now you want to stay close to the point, because there might be like an S curve going on that you don't want to get caught on. So you want to keep your values close to, and maybe I'll make a note here. Keep test points close to the vertical asymptotes. Okay, so we've got -1.9, and I'll write out our 2x minus 1 times x plus 4 again, over x minus 1 times x plus 2. It's just nice to be able to see plugging it in every time. Or if you don't want to write it out, you don't have to. You can just do your positives and negatives. So 2 times -1.9 now is still going to be roughly -4, and then -1 is still negative. -1.9 plus 4 is still going to be positive, over -1.9 minus 1 is still going to be negative. The only difference here is -1.9. So now I'm on the right of -2, so just slightly less than -2. So then when I add 2, I actually get to a positive number. So that's the only difference here. So I get to a positive number. So now I have a negative over a negative, which makes a positive. So this becomes a positive. So what that looks like is, okay, so now at -2, I have this kind of behavior. So from the left, it's heading down to -infinity, and from the right, it's heading to positive infinity. So here might look something like this. Even though I'm drawing it below the x-axis, that's not necessarily true, but I am just kind of sketching out the general behavior here. So now we're going to do the exact same thing, but around +1, right? So remember, heading into 1 from the left, again, let's just pick some values because it's way easier to think about values, right? And then what's nice is you don't have to actually do the calculations. You can just kind of think about the behavior. So let's use 0.9 here, and maybe let's use 1.1 here. Right, just kind of in our minds. So, oh, I had a little panicky moment. Did I hit record or what? I did. So, because this is a big section, right? So, all right. So we've got our 2x minus 1 times x plus 4 over x minus 1 times x plus 2. Now imagine putting in 0.9. So 0.9 is basically 1. So 2 times 0.9 minus 1 is going to be positive, right? And you can check it on your calculator, right? That's one that I'm not, expecting you to be too sure about. But if you do it, you end up at 0.8. So okay, so it is positive. So it becomes positive times, and then 0.9 plus 4 is still going to be positive. And then 0.9, so now remember these points, -2 and +1, they came from where they make the denominator 0. So just like we had that switch around -2, we might see that same switch around 1 now. So this is the one to watch, right? X minus 1, because that's where we get this vertical asymptote from, 1, right? And so now, okay, I'm from the left of 1, so 0.9 minus 1 is going to be negative, right? And then 0.9 plus 2, that's going to be positive. So overall, I have a positive times a positive is a positive divided by a negative times a positive. Overall, that's going to be a negative. So here, the behavior that we're going to see here is heading down towards -infinity. Right, and so here, maybe I'll just clarify, oops. -infinity, right? Because this is where the negative came from. In case that wasn't clear already. There. Okay. I know there's a lot going on here. And like I said, this is the hardest part of these questions, but once you have this under control, and honestly, you can always check with Desmos, right? So you can always check your work, make sure that what you did makes sense by graphing it in Desmos. So let's see here, 2x minus 1 times x plus 4. This is our last one. X minus 1 over x plus 2. Now I'm pretending to be at 1.1, let's say. So 2 times 1.1 minus 1 is still going to be positive. And then 1.1 plus 4 is positive. 1.1 minus 1 is positive. Right, that's going to be the ticket there. And then 1.1 plus 2 is also positive. So overall, I have a positive behavior here meaning it's going, oh, not curve like that, to positive infinity. Okay, good. So let's go to our next step, and this is our last step before sketching, right? And so let's find the horizontal asymptotes. It's a lot more fun than the vertical asymptotes. So here we go. I need this. Oh, no, I need this. Sorry. Because we need to compare the leading terms for the vertical asymptotes. So horizontal asymptotes, don't listen to me. All right, so step 4 is the horizontal asymptotes. Okay, and I'll just bring in r of x again. So here I want to highlight that n equals 2, right? So the degree of the numerator is 2 and m equals 2. Okay. And then I also want to look at an equals 2 and bm equals 1. Right, if there's no visible coefficient, you're multiplying by 1. Now, since, right, and the reason that I looked at these leading coefficients is because I have the same degree here, right? And if you refer back to our notes or from just in the review, right, if n equals m, so here I'll say since n equals m equals 2, right? So they're all equal to each other. We have a horizontal asymptote at 2 over 1, right? And don't be confused by this 2 versus the degree here. We have a horizontal asymptote at an over bm, which is 2 over 1, which is at 2. So y equals 2 is a horizontal asymptote. Okay. So what I want to do is now I'm ready to put all this into action, right? And so here, step 5 is to sketch this thing. And let's see here. I'm going to try to give myself quite a bit of space here. Who knows if I'll be able to pull it off. All right, so what I want to do is I want to take all the information from all the steps that we just did, and I just want to put them on the graph, right? Specifically starting with the x and the y intercepts. So let's start there. So we've got our x-intercepts at, is it? Okay, at -4 and 1/2. And while we're here, right, the y-intercept is at y equals 2. So I'm going to plot those on here just as dots, right? They're just points. So I had at y equals 2, that's our y-intercept. And then we had, let's say here at -4, I had an x-intercept, and then trying to do my best with the scale here, but it's not going to be beautiful. And remember, it's just a sketch, so the scale doesn't have to be, you know, perfect. Okay, so now I've got my x-intercepts and my y-intercepts. In fact, I'm going to write them as ordered pairs here, right? The x-intercepts are where y equals 0, and the y-intercept is where x equals 0. All right, so we've got our intercepts. What was our next step? The vertical asymptotes, right? So we had vertical asymptotes at -2 and 1, and we already know the behavior around here, right? So they've got this kind of, oops, going the other way, that behavior. Okay, so at -2, which kind of halfway through here, and at 1, which I'll put there. Okay, so what I want to do is I'm just going to put an imaginary asymptote here. Oops. You know what I just remembered? I can do a dotted line. I just do fancy, right? Because those are just imaginary asymptotes, right? So I'm going to start just drawing those vertical asymptotes. Same thing with the horizontal asymptote. And then I'm going to start to piece things together. Okay, so our horizontal asymptote was at y equals 2, which happens to be our y-intercept as well. Let me just check to make sure. Sorry. Okay. All right. So at y equals 2, again, we've got this horizontal asymptote. Oops. How come it? There. And here we have vertical asymptotes. There. Okay. So what happens here is, okay, the horizontal asymptote, it describes the behavior as x is going to infinity, right? So the horizontal asymptote, and what I kind of reacted to here, shouldn't have, but it's okay. Lesson learned, right? You can cross the horizontal asymptote, you can cross an asymptote as long as you're not out towards infinity, right? So as you head towards negative infinity and positive infinity, then yeah, you should plateau around the horizontal asymptote. One thing to remember is you could come from below, or from above rather, or you could come from below. We don't actually know that yet. Okay. So let's see here. I need to draw a line that goes through these points, right? -4 and 1/2. Now, I also know the behavior around these vertical asymptotes, so I need to translate that as I do the sketch. So what I want to do is, okay, around -2, we said I have this going to negative infinity and heading up towards positive infinity behavior. Sorry, it's really slow to catch up here. Now I'm going to go back down. Yikes. Maybe I should just use the whiteboard tablet that Kate has going on. Oh, I copy paste too much for that. So what I need is eventually, right, overall, from the left, this thing is going to negative infinity. So it looks to me, and remember, this is just a sketch, right? We're not, drawing this thing perfectly. I'm just trying to get an idea of what a reasonable graph would be. And then I will say here, I do want you to confirm with Desmos. Confirm using Desmos. Okay, so, but it's really important, especially when you head into calculus, right, to be able to have an idea of what these complicated things might look like. So I know I'm heading down towards negative infinity here. I know I have to cross through this point, so it seems reasonable that I would plateau off underneath the horizontal asymptote. So I'm just going to draw that in one, or try to draw that in one line. Uh-oh, that didn't go well, did it? How about like that? Ish. Okay, so here, kind of plateauing around that horizontal asymptote. Good. So now moving on to the next section, well, I know overall I have this kind of going to positive infinity behavior, right? So that's how I know I'm behaving around -2 from the right. I also know that I have to cross through 0, 2. But then I also have to cross through the 1/2, the x-intercept. And then I also know that I'm heading down towards negative infinity, I think. Let me just confirm. I am. So here I know that once I cross over, I'm heading towards negative infinity, right? And then I'm heading to positive infinity. So just to graph these vertical asymptotes here, now I can see where this graph must go, right? It must cross through the y-intercept and then head through the x-intercept, probably a more beautiful line than that. Let's see if I can pull it off. Probably a little bit smoother than that, but that's the idea. And then the last part is a little bit sneaky, right? Because, well, I know the behavior around the vertical asymptote. I know I'm heading towards positive infinity. We just confirmed that. So I know I'm heading to positive infinity. I also know that I have this horizontal asymptote. Now, the thing is, there are no more x-intercepts. There are no more points where this thing would cross the x-axis. So this is the only kind of hard part about this sketch, is that this sketch would just kind of drop down onto the horizontal asymptote because there are no more x-intercepts. If we had more x-intercepts, right, we would need 2 more to kind of come up again and go to the horizontal asymptote from below. So, but we don't have that, so now I'll sketch my graph like that. Now what I want to do is I want to confirm this using Desmos, and you can use your factored version. I would recommend using the original version of the graph or the function, and then maybe also sketch the factored one to make sure that they're the same, right? They'll be overlapping, so you won't be able to see a change, but that's a good thing. And then let's also confirm what we've done here. So where is that Desmos? All right. I'm just going to grab our function here. We had, and because I want it all in the numerator, I have 2x squared plus 7x minus 4 bracket divided by, and then it's x squared plus x minus 2. Okay. Hey, look at us go. Can you believe it? This looks a lot like what we did, right? So yeah, we're crossing it at all the right points, and we even figured out the behavior of this little guy, right? Because it's heading towards positive infinity around 2, and then, or around 1, sorry. And then I guess kind of hanging out on top of the horizontal asymptote. So now, just to confirm, right, let's make sure that when I sketch the graph of 2x, so now I'm doing the factored one, just to make sure that they're the same. 2x minus 1, right, just the way to check your work, times x plus 4, and I'm just grabbing it from my notes here, so hopefully it's okay, divided by x minus 1 times x plus 2. Notice that they're overlapping, right? So I hit the blue one and it's blue, and then I hit the green one and it's green. And because they're overlapping here, we have the same graph. So, okay, now I have to remember, I'm learning how to bring in insert last image. Look at me go. So here we have, but it's just a screenshot of the graphs. And since these two since the original function is overlapping the factored function, they are the same, right? That's a good way to check your work initially, right? I always like to use Desmos as a crutch, right? If I'm not sure where I'm headed, you'll still need to show the work of finding the behavior of the vertical asymptotes, but at least if you can sketch it in Desmos to get an idea of what you're looking for, I always find that that's a bit of a boost, right? You're heading towards the right answer, right? So so definitely go ahead and just use Desmos. This stuff is tricky, right? So that was that one. There were a couple of other scenarios that I wanted to walk you through. How are we feeling? Do you guys want a break today? I'm just blabbing. That was a big question. So let's see here. How about we just have a quick, yeah, need to caffeinate. So how about we just do a quick break, until 9:10. How about 11-ish? Keep going here. But yeah, good call. So you do have your test 2. I just have to make sure. I don't know, all the days are just getting away from me. I don't know. It's like tests everywhere. I know, test 2. No, thank you. It is on Tuesday, right? And it will be up until the material that we cover on Thursday. So we are going to get into exponents and hopefully logs. Maybe we'll even be able to start a little bit today, but I did want to take our time with this stuff that we're doing now, because it can be tricky, right? So so I wanted to kind of take our yeah, so it's not including test 1 explicitly, but just so chapter 2 and 3 for sure, and then Oh, and lines, right? We had lines, so maybe I should put this, I'll reiterate this stuff later, but test number 2 is on March 30th, which sounds like a long ways away, but it's not. And it's going to cover 1.10, which is on lines, and then chapter 2, right? And I will say after test, oops, oh my gosh, after test number 1, right? Chapter 2, and then 3.2, 3.3, and 3.6, which is what we just did today, right? So I'm calling it chapter 3, but and then up to material covered by the end of Thursday this week. Okay. What's nice is the material that we're about to head into is a lot easier than what we have been doing, or at least in my mind, it just flows nicer. It's easier to deal with. So that's a nice thing. And practice test will be available on WebAssign. And that's the same as the other practice test for test 1. So not for marks, but maybe what I'll actually scratch that. It's not going to be for marks explicitly, but I'll use it as a bonus assignment. So if you do it, I'll replace your lowest assignment grade with that practice test. If you don't have time to do it, or if you don't want to do it, or whatever, then that's okay. You just don't get the bonus. Do you have assignments to do this Friday? Probably. I'll have to have a look. Probably the 3.2, 3.3, and 3.6 assignments. I'll have to have a look. Or if someone's on there, let me know. Okay, yeah, so assignments, and I'm actually going to keep them that way because they're on the test. I want you to be working on it now, especially 3.6, the stuff that we're doing right now is, hey, look at you go, Wendy, can be really tricky, right? And so I want to keep them for Friday, just so you can be prepared and use that as practice for the test. So assignments up to 3.6 are due on Friday. Right, and definitely use those as practice. But I will post the practice test as well, and just like test 1, it's going to be a good indicator of how to prepare. Or actually, I think test 1, is that the one I threw you guys for a loop and I had a bunch of different ones? There's only going to be one practice test, and it's going to be very similar to the actual test. Yeah, scratch that. I didn't do that for test 1. Usually I do, and I will. So the practice test, just use it. It is just a practice. It's not practice for the test anymore. Sometimes I want to have different versions of the same type of problem, so it might be a little bit longer than the actual test, but I'll have a look closer and we can talk about it on Thursday. Okay, so I'm actually going to bump this page to the top because in the notes because no one's going to find it if it's in the middle. But it's important. Okay. So decisions. There are a couple of kind of scenarios where we might have to go a little bit deeper for our sketch. So let's see here. I'm looking at number 59. Okay, so copy, because I don't want to. Bring in that whole question because it takes up a lot of space. But so here, let's do another problem. And this one's going to be a little bit different because we have multiplicity. Okay, so first step is we have to factor this thing. And this one's not so bad. It has to add, so the numerator, right? So step one. Step one, factor. So R of X is, now for these little guys, I'm just gonna, you can use the quadratic formula if you want, right? It's a quadratic, you'll be able to find it, or it has to add to -2 and multiply to +1. So I'm gonna just go out on a limb here and say that that's x minus 1 times x minus 1. And just make sure x times x is x squared, okay? Minus x, that's minus 2x, and then -1 times -1 is +1. So, okay, works out. And then for the denominator, again, it has to add to +2 and multiply to +1. So let's just try x plus 1, oops, times x plus 1. Okay. You can check it, but it works out. Okay, so what we can do is we can rewrite this as R of x then is x minus 1 squared over x plus 1 squared. Okay. Multiplicity 2 behaves in a special way. Okay. So that's one thing that we need to kind of keep in mind. Okay. Let's see here. I'm going a little bit quicker because what the goal of what I'm trying to show you is this multiplicity of 2, right? And so it's from the section 3.2. So we talked about it in 3.2. And if we have multiplicity m, and m is odd, then it crosses the x-axis. If m is even, so now we have multiplicity 2, right? So now m is even. So now we're going to have this kind of bounce off the x-axis situation. So I'm going to bring this in again. And this is from section 3.2. We have this, right? And so here, we're going to have this kind of bounce off the x-axis situation. So our x-intercept, so let's just keep going through the steps, remembering that we have this multiplicity and it's going to be a little bit special. So step 2 is our intercepts. Oops, intercepts. Your x-intercepts are where the numerator is equal to 0, right? And so that's where x minus 1 squared equals 0. Okay. So now I'm not talking around it so much because I'm just trying to show you some different scenarios. So that's going to happen when x is 1. Multiplicity 2. Okay. So we only have one x-intercept, right? And that intercept happens to be at multiplicity 2, which means that at 1, we're going to have, if we're facing up, then we have this kind of bouncing off facing up, or we might be facing down. So we do need to look into that and see what's going on. But so we have a multiplicity 2 at x equals 1. So it behaves just slightly different. The y-intercept is when this thing equals, or when x equals 0. So it's when r of x equals 0, or r of 0. R of 0 is 0 minus 1 squared over 0 plus 1 squared, which, trying to keep it on the same page here, negative 1 squared is 1, and then positive 1 squared is 1, so 1 over 1 is 1. So our y-intercept is at 1. Now for our step 3, the vertical asymptotes. Okay. That's where the denominator is 0, right? And again, we have, let's see here, a denominator equal to 0 at negative 1, right? And so that's the only time that x plus 1 squared equals 0 at x equals negative 1. So we only need to check the behavior around negative 1. So here we go. I'll put negative 1 here in the middle. It doesn't matter where you put it. And so let's see here. Kind of a simpler scenario. Here I want x to head towards negative 1 from the left, and on this side I'm going to head towards negative 1 from the right. So again, just picking kind of values close to negative 1. Negative 1.1 is to the left, and negative 0.9. Just remember for negatives, right, the closer to 0 you are, you're on the right. Right, so just kind of keep that straight in your head. And then r of x, the factored version of r of x is x minus 1 squared over x plus 1 squared, which if I'm pretending to be a negative 1.1, then as soon as I'm squaring anything, right, then I'm going towards a positive, right? So it doesn't matter what values these are, negative 1.1, but you should still check them, right? Negative 1.1 minus 1 is going to be a negative, but then when I square it, it becomes a positive. Positive over negative 1.1 plus 1 is just slightly negative, but then when I square it, it becomes a positive. Positive over a positive is a positive. And then same thing. So that means that as I'm coming in from the left, I'm heading up towards infinity. And here at x minus 1 squared over x plus 1 squared, well, if I'm at negative 0.9, I get negative, but then when I square it, I'm at a positive, and then again, I'm at a positive. So overall, I have this heading to positive infinity from both sides. Okay. Step 4, we're looking at our horizontal asymptotes. Okay. So now I need to refer back to our original function. They have the same degree, right? X squared and x squared. So they have the same degree. So then we refer to our little handout, right? If they have the same degree, then I look at the leading coefficients and I'll have a horizontal asymptote at the ratio of the leading coefficients. So I'm going to copy this here. Mostly so I can just write it out again here. R of x equals x squared minus 2x plus 1 over x squared plus 2x plus 1. Now I can remove that, bump it over. So I've got n equals 2 equals m. Right, so I have the same degree, and I have an equals 1, and well, these look like zeros, I guess. And bm equals 1. Therefore, y equals an over bm is 1 over 1, which is 1, is a horizontal asymptote. Okay. So now we've kind of wrestled up this information, right? We went a lot faster this time around, right? And so maybe take some time to kind of make sure it makes sense. But now if we go to sketch this thing, what does it look like? You're going to combine all the information that we just found, things like the x and the y-intercepts, right? I think we had an x-intercept at, let me scroll back there, at 1. And remember, we have multiplicity 2, right? And then we also have the y-intercept at 1. Lots of 1s going around, okay? And we have the vertical asymptote at -1. Okay, so here at 0, 1 is my y-intercept. My x-intercept is at 1, 0. And I have a vertical asymptote here at -1, 0. And I'll change. So it's kind of a dotted line here. And then, so this is the vertical asymptote. And then we also found that at y equals 1, which again, it just happens to be the same as the y-intercept. That's not necessarily always the case, right? So here, I'll draw my horizontal asymptote. And this is my vertical asymptote. This is the only place that I hit the x-axis. So that tells me something about the behavior on this side, right? Because I know what happens around this vertical asymptote. I only had one to think about. So I already know, because we worked on it, right? I already know that I'm heading up towards positive infinity around both sides, right? So what that means is, because I'm not crossing the x-axis at any other point than at 1 potentially, it means that this thing on the left-hand side is going to just plateau off on top of the horizontal asymptote. So here it's going to look kind of like that. And then I know I have to hit, so I have to go through the the y-axis at 0, 1. I also know that I have the x-intercept at 1, but it has to bounce off, right? Because it's multiplicity 2. And then eventually I have to hit this horizontal asymptote or approach the horizontal asymptote. But because I'm coming from the x-intercept here, it makes sense that I'm coming from down below. So I end up kind of looking like that. And I should show more curvature. So what happens here is I want to make sure that it looks like a parabola bouncing off. And this is what multiplicity 2 looks like. Bounces off. You can check that in Desmos, but I think it looks pretty good. Let's check it just in case. Oops, I want to wrap my numerator in brackets just so it's all being divided. Where is that function? I'll do the original function, so x squared minus 2x plus 1 divided by x squared plus 2x plus 1. Looks good. Looks like what we found, right? Just make sure. Oops. Hey, heck. That's not exactly what we found. Did we type in 1.25? Oh, minus 2x. There, I had typed in the equation wrong. There we go. Now I feel like I can try to screenshot this in here. So it does look like what we just found. Although theirs obviously is a lot nicer looking. Mine's all jaggedy. Okay, so the last thing that I want to talk about in this section is common factors. So we've been assuming that that p of x and q of x don't have any common factors. But if they did, what happens is that you would get a hole in your graph. So we have assumed that p of x and q of x do not have any common factors. Do not have any common factors. If they did, our graph would have a hole. If they did, our graph would have a hole. For example, if we think about something like s of x equals x minus 3 over x squared minus 3x, notice that I can pull out a common factor of x here. And so then what I get is I get x minus 3, which I'll wrap up in brackets just to illustrate, over x times x minus 3. So now notice that I have these, That's not what I meant. I have these x minus 3 common factor. So now what we can do is I can cancel these, that's allowed, right? We can cancel. However, we still need to make sure that I don't have x equals 3, because then I would be dividing by 0 in the denominator, right? Or I would have 0 in the denominator. So you can cancel these, but the domain still has to reflect the original function. So we can cancel x minus 3, but the domain still needs to reflect the original function. Okay. Which is, so the domain here, or maybe I'll write it out again. So if s of x is x minus 3 over x times x minus 3, well, it's been a while since we did the domain here, but the domain is that x can't be 0, right? Remember, I have to avoid dividing by 0, so x can't be 0, and x can't be 3. So that domain still stays the same. So even when we find that s of x is x minus 3 over x times x minus 3, even when I cancel these, and I find that s of x can be written as 1 over x, right? The domain is for x not equal to 3 and x not equal to 0. But the not equal to 0 is obvious from the function, right? So what I need to emphasize is that x equals 3 has to be pulled out of the domain because it doesn't work in the original function, right? And our graph would have a hole. Our graph would have a hole at x equals 3. Okay. That's just something to keep in mind if you're canceling stuff, which won't happen often, right? But if you are, then you need to kind of put the brakes on and say, okay, well, my domain has to be from the original function. So let's just graph this to see what it looks like. So we have, I'm going to wrap it up in brackets, x minus 3 divided by, and I think it's x squared minus 3x. Remember, I use the original function just to make sure that I'm graphing the right thing. So now, here looks fine. Looks like 1 over x, right? Except when I hit x equals 3, it's undefined. I'm trying to hold it there. So that's why it's not obvious, right? From the graph, you have to kind of scroll around x equals 3, but then we see the hole. Do I dare try to screenshot this? I'm going to turn off my iPad. No, it's too hard. I have to like do a little pinch. Okay, good. So in preparation for next day, okay, I want you to have a read through the chapter 4 notes, ideally all of them, but definitely 4.1 to 4.3. So on Thursday, or sorry, to prepare for Thursday, read the 4.1 to 4.3 handouts. Because it's always good if, when you hear it from me, if it's the second time that you're hearing or seeing this stuff, right? And so then it won't be so out of the blue. So we're starting this new chapter, and it's on exponential and logarithmic functions. So chapter 4 is on exponential and logarithmic functions. So I'm not going to start this chapter because we don't really have time to start anything new, but I do want to, oh, I didn't spell that right. Next day I'll take it slow. Logarithmic, there, functions. So we call them exponents and logs for obvious reasons. It's hard to say. But just to give you a preview of what we're doing. So exponential functions are just another type of function that we're introducing. So we've kind of beaten the quadratic function a lot, right? We've used it a lot. So now we're just introducing another function that we need to know the shape of. So exponential functions are kind of this exponential growth, and we use it a lot for modeling populations, money growth, and things like that, like exponential growth. You might have heard of that just in real life because it's a real thing. And then what's kind of nice is we've already talked about the inverse of a function. Okay, so logs are the inverse of exponential functions. And so that's what I need you to keep in mind, is that they're definitely related, and to undo one, you need the other. Logs are the inverse of exponential functions. So it's good because we've already talked about inverses, right? And so inverse of a function, and so we need I'll just do EXP, exponential functions, to undo logs, and we need logs to undo exponential functions. Okay. So I need you to read through those, just the handouts. You don't have to read the whole chapters, right? But just the handouts, just so we can jump right in and get started. Because it turns out we're ending a little bit early today, and it feels weird, but you're free. Any questions before you go? None. 3.6, it's a doozy, rational functions, but it's over now. All right. If you do have questions, let me know. Otherwise, I will see you on Thursday.